This is a question I've got about marking. It goes like this. My tutor showed me some ways of proving trigonometric identities that have left my teachers at school divided as to whether it should receive full marks. They are, consider left-hand side divided by right-hand side, and show that left-hand side divided by right-hand side equals 1 through simplification. Hence, left-hand side equals right-hand side. I guess because, in theory, if you take this line and then multiply both sides by the right-hand side, you cancel it over here and the right hand side appears over here, which is how you get this, which is what you're trying to prove. That's suggestion number 1. Suggestion number 2, consider left hand side minus right hand side and show that left hand side minus right hand side equals 0 through simplification, and hence instead of multiplying by right hand side, you add the right hand side to both sides, and that's how you get this. We'd love to hear your thoughts on whether you think it would be a valid full mark solution in an Extension 1 exam. Okay, thanks for writing. I guess the first thing I want to say is what I'm about to give you is my opinion and nothing more. So, you know, it's not something that I would use in an argument really, but just in case you're curious, this is what I think. My second comment, by the way, is not just that you've got these two choices here, but my definite preference would be if what you were required to prove was, and then they give you a statement, left hand side equals right hand side. Okay, I think the definite preference would be to say start from one side or the other, and it doesn't matter which one, and say, okay, well, you start with the left hand side and then you say what it's equal to, and if you can do all of the algebraic manipulation required to do either of these proofs, then you should be able to simplify whatever is here, blah blah blah, 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 and then eventually get to the other side, from one side to the other, rather than trying to consider sort of some kind of different situation. I think this is what's preferable, and I've demonstrated that in my videos tons of times. So, I think this is the clearest way to prove it, and always the preference, but that said, here is my opinion on these two methods that you've mentioned. I'd accept number 2. I think number 2 is sort of a goer. But I'd recommend strongly against using number 1. That's not to say it's wrong, but I don't think it's a good idea. Now, the reason why I dislike number 1 is because division in here, it's a dangerous thing when it comes to functions. So composite functions involving division, they have restrictions, and let me show you what I mean. If I were to consider two different functions, let's go, let's get a new piece of paper here. Okay. So if I considered f of x, let's say that graph there. Okay, and this is pretty simple. It looks like this. Okay, here's your axes, and everyone knows what y equals x, or f of x rather. If I make that the f axis and this is the x axis, that's what it looks like. No problems. Okay. But if I were to say consider a similar function, something like this, x squared on x, simplification would tell you, sorry, let's give that a different name, let's call it g. Simplification should tell you that every time you sub in a value, you'll get the same graph as what you have over here. Simplification should tell you that algebraically, but every value works except for one, namely x equals 0. X can't equal 0. You put it in, you get 0 divided by 0. And so at the origin, there's a hole there, there's a gap. And then the rest of the graph does look the same. So these two functions, f and g, I know they look very similar, but because of the division that's been introduced here, they're not the same, okay? And, you know, this problem kind of creeps up all the time when we're doing, you know, t solutions, t methods. So when you say, let t equal tan theta on 2, and then you get your result for sine theta, and your result for cos, and so on, right? When you have an equation and you're solving it in terms of sines and causes, that's fine, but when you introduce t, you see, tan is a reciprocal. Sorry, not a reciprocal. It's a ratio between sine and cos. So you've introduced a division of a function, right? So if you were using this method, right, you're going to get holes in it, and that's why you have to test. Let me bring this up a little bit. That's why you have to test other values, namely theta equals pi, right? Because when theta is equal to pi, tan theta on 2 is undefined, even if the rest of the stuff that was in your original question is defined. So therefore, this idea here, consider left-hand side divided by right-hand side. Well, yeah, you gotta be careful with that, right? For all intents and purposes, with the trig identities that you get, this will probably still be true. But I think it's a bad idea to introduce division where it's unnecessary because of things like this, introducing these holes, places where the solution doesn't exist. Okay. Now, number 2, this consider left-hand side minus right-hand side. That's a much safer option, I think. In fact, it's used in proving inequalities all the time. So if what you were asked to prove was something like this, if you're asked to prove A is greater than B, a very, very common thing is to say, well, let's consider A minus B, and then you do some algebraic manipulation with it, blah, 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 until you get something over this side, which you can clearly say, oh, look, that's positive. You know, for instance, maybe you manipulate in such a way to show that it's a square number, and that it can't be equal to 0 either. So once you establish this, you see, in terms of functions, adding and subtraction are much safer than multiplication and division, because they don't introduce any of those restrictions that I mentioned before. So I think this would definitely be accepted with full marks. Like I said, it's all just my opinion, but I hope that makes sense.